Unit 1 of the Advanced Higher Chemistry course is Inorganic and Physical Chemistry, and the first part of Unit 1 is about electromagnetic radiation and atomic spectra, and in this first lecture we're going to focus on electromagnetic radiation. The learning outcomes for this lecture are that you should be able to state the relationship between the speed of light, frequency and wavelength for electromagnetic radiation, and you should also be able to recognise the different types of electromagnetic radiation. We come across electromagnetic radiation every day in our lives. Light, visible light for example, is a form of electromagnetic radiation. Red light, orange light, blue light, and other things like infrared, ultraviolet light, X-rays, gamma rays, microwaves, radio waves. These are all different forms of electromagnetic radiation. So what exactly is electromagnetic radiation? Well, it's a form of energy, and it can be described in the form of a wave. So in order to understand all these different types of electromagnetic radiation, we need to go back and remind ourselves about properties of waves. Okay, so there's a wave, and all waves can be described by three properties. That is the speed of the wave, how fast it's travelling, its wavelength and its frequency. So some waves can travel slowly, some waves can travel very fast. But that's not the case when it comes to electromagnetic radiation. One thing that all forms of electromagnetic radiation have in common is they all travel at the same speed. So the speed doesn't vary between radio waves and blue light and gamma rays. And the speed they travel at is the speed of light, which is 3 times 10 to the 8 meters per second. So all electromagnetic radiation travels at the speed of light, which is 3.0 times 10 to the 8 meters per second. So the speed is given the symbol c. The next thing you use to define a wave is the wavelength, which is just the length of one complete wave. In a diagram like this, you normally measure it from the peak of one wave to the peak of the next wave. So that distance there is the wavelength. So it's the length of one complete wave. In the Advanced Higher Chemistry, the part of the electromagnetic radiation spectrum that we're interested in, we tend to measure the wavelength in nanometers. So very often you'll come across a unit nanometer. So 1 nanometer equals 1 times 10 to the minus 9 meters. The symbol for wavelength is a Greek letter, lambda. Okay. And the frequency is the number of waves that pass a fixed point in 1 second. So imagine this wave's travelling from left to right, and you counted the number of complete waves that pass this point here in 1 second. So it's the number of waves passing a fixed point in 1 second. So a wave moving slowly, maybe only 2 waves, 2 complete waves pass a fixed point in 1 second. Or maybe it's faster moving and 100 waves pass a fixed point in 1 second. So if it was 100, you would write, so the frequency is 100 per second. So 100 waves pass per second. Or sometimes we use the symbol hertz. The number would be the same between per second and hertz. So the Hz stands for hertz. Okay. And frequency is given the symbol F. Okay, let's look at a couple of waves with different wavelengths and frequencies. So there's one wave, and here's another wave. Okay. So in terms of wavelength, so wavelength here is from there to there, so it's quite big. So this one's got a big wavelength, whereas for the second wave here, wavelength is just from there to there, so comparatively small compared with the top one. If you look at the frequency, now imagine these are both different forms of electromagnetic radiation, so both the waves travel at the same speed, speed of light. So because this top one has got a long wavelength, in some given unit of time, the number of waves that are complete waves that are going to pass a fixed point is going to be relatively small. Whereas if this wave's travelling at the same speed as this one, far more complete waves will pass a fixed point in a fixed unit of time. So you get this inverse relationship between the wavelength and the frequency. If electromagnetic radiation has a big wavelength of a small frequency, and if it's got a small wavelength of a big frequency. And that's summed up in the first equation that you need to know, which relates the speed of light, the frequency and the wavelength of the electromagnetic radiation. It's simply C equals F lambda. C is always the same number, 3 times 10 to the 8. So if F is small, lambda must be big. And if lambda is small, F must be big. Now, you don't need to remember this equation, it's in your data booklet. So, on the first page of the data booklet where all the equations are given, this is just a segment taken from it. These are all National 5 equations, and then the first one there, C equals F lambda. So you don't need to remember that equation, it's in your data booklet. So let's look at a couple of questions that you could get asked, which you have to use that equation. So infrared light has a frequency of 3.75 times 10 to the 14 Hertz. Calculate the wavelength in nanometers of this radiation. Okay, so we know C equals F lambda. We've been asked to calculate the wavelength, so we have to rearrange the equation. So lambda equals C divided by F. C is the speed of light, 3 times 10 to the 8. And frequency, 3.75 times 10 to the 14. So remind myself that equals 8 times 10 to the minus 7. Then you need to be careful with units. Well, because the speed of light is in meters per second, the wavelength comes out in meters. In the question, you are asked to give the wavelength in nanometers. So that is equivalent to 800 times 10 to minus 9 meters, which is 800 nanometers. So the wavelength of that radiation would be 800 nanometers. Another example, calculate the frequency of X-rays with a wavelength of 0.65 nanometers. So again, we start off with our C equals F lambda. It's F we want to calculate, so F equals C divided by lambda, which equals 3 times 10 to the 8 And again, because the wavelength is in meters per second, you've got to have your, because the speed of light is in meters per second, you've got to have your wavelength in meters. So it's 0.65 times 10 to the minus 9. Okay. And that comes out at 4.62 times 10 to the 17 hertz. So it's quite straightforward. The main mistake you're going to make is leaving the wavelength in nanometers or not converting it to nanometers depending on the question. So really be aware of that unit. Okay, so we know that electromagnetic radiation is a form of energy. It can be defined as a wave. So what makes one form of radiation different from another? It's the wavelength and the frequency. So here's many different things that are parts of the electromagnetic spectrum, going from radio waves through microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all different forms of electromagnetic radiation. Wavelengths vary over huge orders of magnitude. Radio waves are huge. These numbers here are in meters, so 1,000 meters. So radio waves are in kilometers. As we move to the left, as this diagram shows, the wavelength gets smaller, and gamma rays are at 10 to minus 12 meters. So where you lie on the electromagnetic spectrum depends on your wavelength. The bit that we're going to be most interested in, not exclusively, but the bit we're going to be most interested in is the visible region of the electromagnetic spectrum, going from blue light here to the red light here. Now, it's worth remembering the wavelength of the visible light. So the blue light is about 400 nanometers, and the red light is about 700 nanometers. So if your electromagnetic radiation lies roughly in between 400 to 700 nanometers, then your eyes will be able to detect it. It will be visible light. If the wavelength is shorter than 400, then you get into the ultraviolet, which we can't see. If the wavelength is bigger than 700, then you get into the infrared, which we can't see. One wee trick to help remember the range of the visible wavelength, in your data booklet you'll find, quite near the back, I can't remember the exact page number, a colour wheel which we'll use later on in the course. But if you're forgetting the wavelength range of visible light, see here we've got the red light at 750 nanometers according to this, and then as the wavelength decreases you go through orange, yellow, green, blue, violet, they've got purple, and that goes to 380 nanometers. So equivalent to more or less from about 400 to 700 nanometers roughly is where you get the visible light. So by now you should be able to state the relationship between the speed of light, frequency and wavelength, and you should also be able to recognise the different types of electromagnetic radiation.